Hi, all right, so for this video, we're going to be calculating the impulse based on a graph. So here, as you can see, we have a force versus time graph. So for this scenario, we have Calvin and Hobbes, and it says that their mass is 45 kilograms. We'll need that in a little bit. They're riding down the hill. The hill that they're on is irregular. It slopes up and down and has snow of varying depths and textures. So this is the graph that's based on their force and the time duration. It does say that the initial velocity when they hit the part of the hill depicted on the graph is 11 meters per second. So it does tell us their initial velocity to start off with. So for part A, it says, how do you find the impulse from 30 to 60 seconds? So to find impulse on a force versus time graph, you do have to find the area under the curve. So the area under the curve is from 30 to 60 seconds. So notice how our graph starts at the 30 seconds, 60 is marked here. So we need to find the area for this box here. We know that the area for a rectangle is base times height. So we know that the base is over 30 seconds times the height. You can see that this goes up to 20, so that makes each line a value of 4. So 4, 8, 12, this is at 12 newtons. So 30 times 12 is going to give us 360 newtons times seconds. So the impulse for the first part of our graph, the 30 to 60 seconds, is 360 newtons times seconds. And it is a positive value because it's in the positive part of our graph. I'm going to change colors now and do the next one. So for part B, which 30 seconds time interval contains a net negative impulse? So net negative is just like with net force. So the overall or the summation of the impulses. That means that we actually need to find the area for each portion of the graph. So we can do that by finding the impulse for each 30-second segment. So we know this one already is 360 newtons times seconds. For the next part, for the 60 to 90, this part is a triangle. We know that the area of the triangle is 1/2 times the base. The base is 30 seconds times the height, and we know the height was the 12 newtons. So 1/2 times 30 times 12 is going to give us 180 newtons times seconds. So 180 newtons times seconds. For our next portion of the graph, so from 90 to 120 seconds, it would be this triangle here. So again, area of a triangle, 1/2 times the base of 30. And then the height, our force, the amount of force, it goes all the way down to the bottom, which was at the -20 mark. So our force is -20. So if we put that in our calculator, 1/2 times 30 times -20, that's going to give us -300 newtons times seconds. So -300 newton seconds. All right, for the next part of our graph, from 120 seconds to 150 seconds, we have a square. So we need to find the area, base times height. So that's going to be 30 times our height, which is our force, is again the -20. So this is going to give us -600 newton seconds. For our next part of our graph, from 150 to 180 seconds, you can see that for the entire journey of this line, it is a straight constant slope. So that means that we can assume that this triangle should be the exact same area as this triangle. So those would actually cancel out. If you calculate the area of both, you would have 1/2 times the base. Well, the base is half of 30 seconds, so 15 seconds. Times the height again is the -20 newtons, and that's going to give us -150 newtons. And then if you calculate the area for this top triangle, it would also be 150, but it is positive because it's in the positive part of the graph. All right, so in your calculators, you would first to find when do we have a net negative impulse, because that's what question B is asking us. First, you start with your calculator. So if you plug into your calculator 360 plus 180, you know that the net impulse from 30 seconds to 60 seconds to 90 seconds, those first two areas, is 540. That's positive, so we're not net negative yet. Then our next part was the negative 300, so subtract 300. Well, that still gives us a positive 240, so we're not net negative yet. Our next part, from the 120 to 150 seconds, that was negative 600. So if we subtract 600, that gives us a net negative impulse of negative 360 newtons. So the time interval would be from 120 to 150 seconds. All right, moving on to part C. Part C, what is the impulse from 30 to 60 seconds? Well, since we already saw for all of them, the next few will be very easy. It's just copying down from the graph. So our impulse from 30 to 60 was this area for this box. So that was our 360 newtons times seconds. We solved the impulse from 90 to 120. So from 90 to 120, this is our negative impulse here, the negative 300 newtons times seconds. And then for part E, it says what is the impulse from 150 to 180? So 150s here, 180s here. So we know that the impulse for this bottom portion right here was negative 150. We know that the positive portion was positive 150. So of course, if you add those together, it equals 0. So there is no impulse, or there's no net impulse occurring from 150 to 180 seconds. For part F, using the information from the text above, so all this information up here where we were given the mass and we were given the initial velocity, calculate the final velocity at the 60-second mark. So at the 60-second mark, we want to know the final velocity. Remember, it does tell us that the initial velocity is 11 meters per second, and our mass was 45 kilograms. So to find this one, we know our equation for impulse is that the change in impulse is equal to mass times our change in velocity. So our impulse at the 60 mark, so from 30 to 60 seconds, our impulse was 360. So we can plug in and we find that 360 newtons times seconds is equal to our mass, and our mass was 45 kilograms, times our change in velocity. And remember, that's always going to be final minus initial. So we're looking for the final velocity. So we're going to write VF minus our initial. And it did tell us in the text above that our initial velocity was 11 meters per second. So minus 11 meters per second. All right, so then of course you can divide by the 45 on both sides because we want to get the final velocity on a side by itself. And once we do that, we would have 8 equals VF minus 11. So of course we add the 11, and that tells us that the final velocity at the 60-second mark is 19 meters per second.